So welcome. So this is our one-dimensional motion part 2, and we're going to talk about, well, let's just cut to it. We're going to talk about motion at constant acceleration. The reason why we care about this is because it's highly accessible to us. If we do motion that's not at constant acceleration, then the math gets really hard. So it's simpler to consider motion at constant acceleration as our starting point. Motion at constant acceleration occurs when you have a constant net force. Net force is the overall force. So when I have one overall force that doesn't change, I get an acceleration that doesn't change. And that happens a lot, actually, with things like gravity. There's a classic example of the weight of the object doesn't change. So it's a constant acceleration that's acting on the object. If I had something like a rocket with thrust engines, I could increase the thrust or decrease the thrust. So that journey might not be constant acceleration. If I kept the thrust constant and I was a steady distance away from all planets, then yeah, it would be a constant acceleration because it's a constant force. So I want you to link, actually, because it will be helpful for the future, I want you to link constant forces with constant accelerations, not motion. People link forces with motion because on Earth we need a force to keep moving to overcome gravity. So the tendency is to say, oh, when I have a force, I have motion. But when I have a net force, I have acceleration. When there's an overall force, it must cause acceleration. So we tend to think more in terms of rockets in space because it's a simpler way of thinking about these things. And then we kind of like think about on Earth because it's more complicated, because the friction is involved in Earth. So we're talking about constant acceleration. And to avoid the friction, we're going to kind of turn around and say, don't worry about air resistance when we imagine things moving through the atmosphere. So this is a family of graphs. And remember what we said last time, you've always got to look at the axes. So I have an acceleration versus time graph. Where's my, oh, sorry. Yeah, I did almost everything apart from getting my pen sorted out. Let's go down and get my pen working. Pen, and so this is an acceleration versus time graph, and this is a velocity versus time graph, and this is a coordinate or position or address versus time graph. And here's the issue. When I have a constant acceleration, it means that I am changing my velocity by a constant amount each second. So in this case, this is 0 down here. This is a positive acceleration. And so that means I'm adding a positive velocity value onto my velocity each second. So if it was plus 2 meters per second, maybe now it's plus 4. If it was plus 4, maybe now it's plus 6. If it was plus 6, maybe now it's plus 8. If it was plus 8, now it's plus 10. If it was plus 10, now it's plus 12, and so on. It's a steady step. That's what acceleration is. It's like a constant acceleration is adding the same amount of change in velocity to your velocity each second. So it's like that. Okay, so I expect to see straight lines, sloping straight lines for the most part when I have a constant acceleration. Zero acceleration, if it stays as 0, is constant. So I suppose I can also have the horizontal straight line for velocity. If there was no acceleration, I'd get a no change in velocity as time passes, but it would still be a straight line. But if I get something that changes the slope, that cannot be a constant acceleration because my velocity is changing in time. Then the other thing is, all right, well, let's look at the area under the curve. We said that the area under the curve was displacement, so I have a certain amount of displacement associated with the first second. I have more displacement associated with a second. I have more displacement associated with a third. So if I add those things on, I get one step, I get a bigger step for the second, I get a bigger distance change step for the third, I get a bigger distance change step for the fourth, I get a bigger distance change step for the fifth. And if I look at the math, that's going to be a parabola. So, okay. So I need to be able to recognize those families because the graphs go together. So let me do it the side before I get into this. Let's say that I had acceleration versus time. This is a better graph, actually. And let's have velocity versus time. And then let's have position versus time. Coordinate position, it's all the same thing. I'm going to draw, first of all, let's just take a stereotypical positive acceleration. So I'm going to draw a line like that. And let's say that I started at 0 velocity. Then I would expect my velocities to start from 0, and it would be a positive slope. Straight line because it's a constant acceleration. Positive because this is a positive value. It's not a negative value, it's a positive value. And if I had an even greater acceleration, and again I started off from 0 velocity, I would expect an even greater slope on my velocity versus time graph. If I did not start at 0 velocity, let's say when I started I was a positive velocity, then I would expect to see the same slope, but just starting at a different initial value. So you can see the variations I can make with this. Let's go down here for us. Oh, and then if I did not start at the 0 coordinate, I would start somewhere else, but I would expect to see for those things a upward going parabola and maybe a more curvy upward going parabola for the higher acceleration curve. I can mirror all that with a, let's change the color. I can mirror all that with a, let's do black. I can mirror all that if I happen to have a negative acceleration. And let's say I started off from the 0 velocity, I would get a negative going slope. And let's say I started off at the same position, I would expect to get something like that. And let's say I had a more negative acceleration, I would expect to get a steeper slope. And let's say I would expect to get something that looks like that. So these curves go together, and you should be able to spot what makes sense and what does not make sense. So if you look at these first few, is this constant acceleration? Clearly not, because it's changing, you know. It's like, okay. All right. Is this the velocity time shape you would get for a constant acceleration? It's not, is it? And why is it not? Because it's not a linear. It's a curvy change in velocity with time. The acceleration here is greater than the acceleration there, and you can see that from the slope. So the acceleration is changing. For this guy here, displacement, well, this is one of the problems with curves. They all look the same, but it looks kind of like roughly parabolic, so I would say, yeah, that's a possibility. That would be consistent with constant acceleration. This is clearly consistent with constant acceleration because it is a constant acceleration, and this is consistent with a constant acceleration. Would it be a positive acceleration or a negative acceleration? Would be negative, wouldn't it, because it's going downwards. And then again, this would be consistent with a positive acceleration. I'm not linking these together. I'm saying just is each of these individually consistent with a constant acceleration. So there's not a family. I should make that clear. Cool. So then we do some math, and it's sort of like there's I'm a visual thinker, so I see something coming out of a graph or a diagram. I'm amazed. And the nice thing is the Greeks also saw things out of diagrams. So I just find this is just, but the first time I saw this, I was gobsmacked. It was like, man, you can do science like this. This is amazing. So this is a stereotypical straight line velocity versus time graph. I like the velocity versus time because if I look at the area under the curve, I go to displacement. And if I go to the slope, I go to the acceleration. So it's like nicely in the middle, and it talks immediately about both other things I'm interested in. If I give you a position versus time, I can get to velocity, but then I got to do something to that graph to get me to acceleration. So this is the nice in-between graph. It's a straight line because we get straight lines of velocity versus time when we have constant acceleration. It's not going through the origin because I don't want some kind of like special case. And I can identify my initial velocity when my clock is lower and my final velocity when my time has passed. So there's a little bit of an issue here. I put in 0 and t, but really I'm interested in the time interval, the delta t. And the books sometimes assume 0 is the time when you start and put t down for the final time. And some books put t and t0, and there's a whole bunch of nomenclature on there. So I like to use VF, VI. I like to use delta t, meaning time interval, because that's what you really mean. So as we change textbooks, I don't change my nomenclature because I'm kind of full of myself enough to think that I'm clear with it. You know, they're bright people. They pick it from traditional reasons. Or I started with V naught, T naught. That's the way I was taught, and I think it's a bit obscure. Okay, so this is a straight line graph. So y equals mx plus b. So, okay, what does y stand for? Well, y is the answer, and y would be vf. So just do that translation. And then m, well, m means slope, and the slope of a velocity versus time graph is the acceleration. And then x, well, x is your value here, and it's compared with the value there. I'd prefer to call it delta t rather than t, because delta t says if you don't start at 0, you've got to still go this far away, whereas t's assuming zeros at the other end, and very often we don't have 0 as our starting time. And then we have, well, what's our y-axis intercept is v initial. Rearrange it. Vf equals vi plus at. That's one of your 4 classic kinematic equations. Learn it, because it's, you know, something like this is going to come up. Okay, that was nice. We got an equation of motion out of it. Equations and graphs are 2 ways of representing the same thing. And again, that wasn't something that was obvious to me when I first began. I kind of thought graphs were kind of like just representations, but they're more than that. They are graphical calculations. And I thought that somehow if I rearrange the equation, I guess never thought about it, but if I rearrange the equation, will I get the same graph? Yeah, of course I'll get the same graph, because it's the same relationship. So they're just 2 ways of representing the same relationship. So every graph has an equation, and every equation has a graph, and you know, they're both pretty good. Trapezium. Well, the trapezium, or you call it trapezoid, I guess. I've been here 31 years. I guess I should call it trapezoid as well by now. But so trapezoid is basically the shape where one line is bigger than the other, and you know, you got a gap between them. And basically, the way that you figure out these things is you say, well, it's the average height. If I cut off that top little triangle and moved it down here, it would be a nice rectangle. And the rectangle would be the average height times the width. So let's do that. So we say it's the left-hand height plus the right-hand height over 2. That's the average height multiplied by the width. And so I put it into kinematics language, and I say, well, the area under the graph, which is what I'm trying to find out, is the displacement. And the average is a half. VF and VI is my 2 things, and then the width is delta t. So I end up with my second kinematic equation. Delta x equals half VF plus VI bracket t. And then let's do a third way. Well, that worked well. Let's say that we want to take this area, but let's represent it as a rectangle plus a triangle rather than a trapezoid. So I have this like shape here. And I say, well, let's have a look for the rectangle. It's going to be the base times the height, where that's the h, from there to there. And then for the triangle, it's going to be half the base times its height. So its height is different. The 2 heights are not the same. The 2 bases are the same, etc. And then let's express that in kinematics language. So I say, well, let's have a look. My answer, which is the area under the graph, is my displacement. And then my left hand, for the rectangle at the bottom, my height is VI, and my width is delta t. Then I put half down. And then for this next bit, I have to do this change in height, which is VF minus VI times delta t. So I end up with this expression, which is correct. but I don't like it so much. And the reason I don't like it so much is because it's not maximizing its power. What I mean by that is that equations, if I have a rearranged version of the same equation, it's telling me the same thing. And I want to be kind of cute here. If you think about it, there's VI, there's VF, there's A, there's delta T, and there's delta X. Those are my 5 parameters that are involved in this kind of motion. We don't worry about temperature. We don't actually worry about mass. These are my 5 parameters. And if you think about it, that first expression compared my VF with my VI and my A and my delta T. It linked those 4 things together, and it missed out my delta X. And this next expression linked my delta X, and it linked my VI, and it linked my VF, and it linked my delta T. So it missed out A. And really what I'd like to do is on the next one, I'd like to miss out something else, etc. And when I look at this, let's have a look. I've got my delta X, I've got my VI, I've got my delta T, I've got my A, and I've got my delta T again. And I'd really like it for various reasons oh, I'm sorry, I looked at the wrong line. I messed it up. Anyway, just go with it. So anyway, I really want to rearrange this a little bit. So what I do is I say, you know, back here, I learned that VF minus VI was equal to A delta T. So if I substitute A delta T for that VF minus VI, I end up with delta X is equal to VI delta T plus 1/2 A delta T squared. And the thing that's missing from there is what VF is missing from there, isn't it? Yeah. And then I do some mathematical rearrangements. It's all there for you. And I get VF squared equals VI squared plus 2A delta X. And what's missing from there is delta T. So with those 4 equations, I've got pretty well all my scenarios covered. And so now here's the trick. Each one of those equations contains 4 things. So as a teacher, I can't work magic. As a tester, I can't work magic. I can't, I'm bound by the laws of math just like you guys are bound by the laws of math. So if I want you to use one of these equations, I have to somehow inform you about 3 of the values and ask you about the 4th. So your job initially, having learned the equations, your job is to figure out which equation do I use. And so I find, especially for beginners, it's kind of useful to recognize what am I not talking about, and then it will help you. My equation cannot have the thing I'm not talking about in it. So with practice, it gets easier and easier and easier. Mathematically, you want to do it using calculus. I'll just leave it for you to do it there. It's all laid out. And it looks complicated. It's not, but it looks complicated. But, it's kind of like again, some people love the abstract, some people love the visual. As I say, I'm just always really surprised when I can do things using a graph and a little bit of thinking. Okay. Let's do an in-class check. At t equals 2 seconds, a blue sports car. So here's my road. And here's my blue sports car. And the time, I'm going to put the little clock underneath it. And it's at rest, so I can say VI is equal to 0 seconds. How do I know that that's my VI? From context. I'll read the rest of it. It's going to talk about some later time, etc. At t equals 6 seconds, so here's my clock at 6 seconds, and here's my car. And it says my velocity, so this is going to be my VF because it's later on, is equal to minus 12 meters per second. And I like to put little arrows on these things, so I'll put that little arrow pointing backwards. For me, that diagram is really, 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 really important. If I don't have that diagram, I can't really figure out what I'm doing. I can't go from the words to a song. I have to go through a diagram. And I think most people are the same way. If you're not, power to you. But if you're getting them wrong, then consider doing diagrams, because I think they'll help. So now I'm looking more at my diagram than I am at the words anymore. And I say, you know, what is the constant acceleration? So A is equal to question mark. So what I do now is I make a list. So I say VI is equal to 0 meters per second, meters per second. And I say VF is equal to minus 12 meters per second. And then we say that my delta T, not my T, my delta T, that's why I don't like using T. My delta T is T final minus T initial, which in this case is equal to 6 minus 2, which is equal to 4 seconds. Most common mistake is people will put down 6 for the time because they're just looking at a final time, you know. And then what I want to find is my A. One time I spent 5 minutes trying to figure out why I couldn't do this problem, and then I realized that I'd not put down what I was actually looking for. And you know, it's one of those slips. I was tired, I was stressed, but you know, when you're tired and stressed, you make those slips. So now I try and write down what I'm looking for on my list. And then when I say I need an equation for this, and you know, at first it's like, oh man, what equation is it? Well, if need be, write your 4 equations down at the side of your page so that, you know, you got them. But basically, with practice, if you do your homework, then you'll get faster and faster and faster. And you go VF equals VI plus A delta T. Now I'm substituting. So I go VF is minus 12. I don't rearrange my letters. I put the numbers in because sometimes a letter will go away because it's multiplied by 0. And it makes the math much easier. If I rearrange a complicated piece of algebra and then put a 0 in it, it's like, man, I did all that work and I didn't need to. So I put the numbers in, and then if I need to, I rearrange. And then this is going to be 0 plus A is what I want, times delta T is going to be 4. So rearranging A is equal to minus 12 over 4, which is minus 3 meters per second squared. So it would be minus 3 meters per second squared. Minus 3 meaning that it's pointing in that direction. The minus is significant. It's a direction. And so we started off with at rest. And we had a negative acceleration, and we went whoosh like that. And so now by time t equals 6, I'm going minus at minus 12 meters per second, whereas here is at 0 meters per second. So I went like that. My acceleration was equal to minus 3 meters per second squared. So I like to, again, it's nice to visualize and just figure out what would this look like. It really helps. We're not doing physics because we're trying to improve our math. We're doing physics because we're trying to improve our analysis of the real world that we see. And eventually the real world we can't see, but we start off with the real world that we can see. And people would sometimes say to me, why do you bother making that list? It's like, man, you know, this test is going to be a long test. Why do I write down all that stuff? And the truthful answer is I make fewer mistakes. By writing down that list, I jog my memory about what equation I'm going to use. And also, when I'm rechecking my answers, I work backwards. So I say, well, does that make up minus 12 over 4? Yeah, it's minus 3. That was right. And where did that come from? Oh, there's the minus 12 there, and there's the 4. So that makes sense. I did the rearrangement, okay. And yeah, the equation, that's that, and that's that. So I check that, and then I can come back here. These are the same numbers that are up here. The more you do in your head, if you make a slip, the harder it is for you to find out and spot that slip. So my advice is get used to writing things down. Imagine that you're kind of like old and forgetful. Write stuff down. You can still get them right. Okay? If you're doing it all in your head, things are fine, but if you make a mistake, it's very hard to find. Then the second thing is whenever, so when I'm doing this, I'm letting you look over my shoulder. This is how I do them. If I'm rushed, I tend to cut corners, and one of the corners I'll cut is that list. And frankly, what I find is that sometimes the equation's not so clear to me. By making that list, by writing down what parameters I have, it's almost like in my subconscious I'm going, oh, I need that, and I need that, and I need that, and I need that, and boom, up comes the equation, because it's familiar to me. So again, it's a lot of this is mathematically, insulting. Yeah, I mean, you've done this for years. It's like this is easy, isn't it? But you can make mistakes on it, and it's clearly not about the math. We know that you guys can rearrange numbers and divide. That's not the skill, is it? It's what do you divide? That's the important thing. So get out of the idea that it's all about the math, because it's not. It's all about what you do the math on. You still got to get the right answer, but... okay, let's do another one. T equals 3 seconds. A red truck has a velocity of +7. So here's my red truck. It's got a velocity VI equals +7 seconds, meters per second. I did that a second time, didn't I? I'm rushing a bit. And the red truck has a constant acceleration. So down here, I'd put down my constant acceleration equals -2 meters per second squared. So my acceleration is going to go down here. And what is the velocity of the truck at t equals 9 seconds? Oh, I didn't put my clock down, did I? So there's my clock at 3. And here's my clock at 9. And there's my truck. And I want to find the velocity, v final. Again, context tells me to call the second times velocity v final. And my first times velocity will be vi, and my acceleration, etc. So again, let's make our list. We go vi is equal to +7 meters per second, and a is equal to -2 meters per second squared, and vf is equal to, I don't know what vf is, and a is equal to -2 meters per second squared. And as I look at this, man, this is good and bad. I'm reinforcing something, but I'm using the same equation. It won't always be this equation. But I look and I say, well, let's have a look. Yeah, that's my VF is equal to VI plus AT. And this time, I'm going to mathematically process it a little bit differently. VF is what I want. So VF is equal to VI is +7 plus A is -2 times delta T. And my delta T was, oh, I didn't do that, did I? I put down A twice. You notice I could recover from that pretty straightforwardly because I wasn't doing stuff in my hand. So it's going to be 9 minus 3. So VF, that's going to be 6. So VF is equal to 7 minus 12, which equals -5 meters per second. Hopefully the answer's there. Yep, -5. So what did this journey look like? I started off with that little guy going in that direction, but it had a negative acceleration. So that was my VI. But my acceleration was in a negative direction. A little bit of shorthand. Actually, yeah, a little bit of shorthand that is correct. What I tend to do is I tend to put my velocities and my accelerations to one side of the object. I put the forces in line with the object. And I don't like to put my velocities and my accelerations on the same level because I really want to keep them distinct. And it's actually, if you have one of those pens with like 4 different colors, they're great because you can have all your velocities as red and all your accelerations as blue and the like. And you'll make, again, it's visually giving you more information, so you'll spot errors sooner. So this is my VI. And what happens is they're going in opposite directions. They're pointing in opposite directions. This is, so every second I add on a negative change in velocity. So this velocity is getting lower and lower and lower until I stop. And now it comes back that way. So when I get my answer, I'm getting a -5. I'm somewhere, let's look, that's +7. I'm somewhere here. So let me tell you a little bit about that. How do I know? Well, if this is at +7, I'm going to be at +6 there, +5 there, +4, +3, +2, +1, etc. Yeah? Because I'm going to slow down as I move to the right. And because it's only using the acceleration due to gravity, what gravity takes away from me as I move to the right, what the acceleration takes away from me as I move to the right, it's giving me back as I move to the left. So I know that there I had 0 velocity. Here I had +1 meter per second. Well, now I got -1 meter per second at the same position on my track. Here I had +2 meters per second because I was moving to the right. Here I have -2 meters per second because I'm moving to the left. Here I had +3 meters per second. Well, I had -3. Here I had +4 meters per second. I had -4. Here I had +5. I had -5. By the time I get back to my starting position, I would have been at -7. Down here, -10, -15. So actually, I can actually draw a reasonably decent diagram of what's going on because I'm familiar. I've become familiar with really what acceleration does. It goes from being a number I put into an equation to being a thing I think about. And the more you can do that, the more you can actually visualize this is what's going on, the easier it gets. It gets easier and easier if you can go to that next level and just get away from, I just substitute into the equation. Cool? Let's do another one. Red truck has a velocity of +15 meters per second when it crosses the starting line. Oh, okay, so here's my starting line. Here's my start. And it's got +15 meters per second, so VI equals +15 meters per second. It's going in that direction. It has a constant acceleration of -3 meters per second, so my acceleration -3 meters per second squared throughout its journey. That means nice constant acceleration. What is the velocity of the red truck when it has a displacement of +5? So my displacement is +5 meters. So what do I know? I know my VI is equal to +15 meters per second. And I know that my acceleration equals -3 meters per second squared. And what do I want to find? Velocity. I want to find my VF. I want to find VF. So what else do I know? Starts there. This displacement equals +5 meters. So now I look at my equations and I go, oh yeah, delta x equals 1/2 VF plus VI. That's the average velocity times delta t. I'm using that equation this time. Is that right? I want my VF. I got my VI. No, that's not the right equation. Sorry. Let's have a look. VF squared equals VI squared plus 2a delta x. Is that right? I want my VF. I got my VI. I got my A. I got my delta x. That'll work. So VF squared is equal to VI squared plus 15 squared plus 2 times A is -3, times delta x, and delta x is 5, plus 5 actually. So VF squared is going to equal 150, or 15 times 15. Got to get out my handy-dandy calculator. Sorry, 725?
No, 225.
225. Yes. Okay, I didn't need my calculator. Nice. Good, good. Thank you. 225 added to, and let's worry about the sign of this. This is 3 2s are 6, 6 5s are minus 30. So that's going to be 195 by the looks of things, yeah. So I get my VF is equal to the square root of 195, which equals, and when I come along here, I go second square root, I go second square root 195, and I'm getting 13.96. I've got to be careful. That's going to be meters per second. I've got to be careful because although that looks like it's the straightforward answer, in reality, square roots have positive and negative roots, and they both work. They do both work. They both have physical significance. And sometimes one of them is more appropriate for our question than the other. If you find a velocity using square roots, but you know that it's travelling to the left, it should be the negative answer. If you find the velocity using square roots, but you know you're travelling to the right, at that point it should be a positive answer. So in this case, I didn't tell you which. I didn't say which one is appropriate. So you really should put down them both. What's happening here is, of course, you're travelling, and you're going out, and then you stop at some point, and you start coming back. And there's the end point, and you cross that point travelling at plus, let's call it 14 meters per second on the way out. You stopped, and then because of the symmetry we talked about before, you cross this point doing minus 14 meters per second on the way back. So both answers are valid. Don't get into the habit of only taking the positive answer, because sometimes the answer you've got to take is the negative answer. Cool. In those examples, I gave you the acceleration, or somehow I should define the acceleration, because it wasn't a given. It wasn't just, I can't just assume it. But in this next set, we're going to talk about free fall. So now we're talking about that family of behaviors where something is, you can't hear that, I'm walking away from the microphone. We're talking about that family of behaviors where something is pulled under gravity. And there's a weird thing, which is that irrespective of how heavy or light the object is, ignoring air resistance, if you let them go, they'll fall down side by side because they have the same acceleration at the same time. And that might seem weird because acceleration is linked to net force, and the net force on this thing is the weight. And so we have a big object with a big net force and a little object with a little net force. And how come they can have the same acceleration? Well, the big object has a big mass, and the big mass is a big inertia, which is a big reluctance to accelerate. Okay, so the big object has a big force, but it's got a big reluctance to accelerate, and the little object has only a little force, but it's got a little reluctance to accelerate. So it cancels out. It's just the most amazing thing, it kind of cancels out. So everything, ignoring air resistance, has an acceleration of minus 10 meters per second squared. Minus 10 because it's pointing downwards towards the Earth, assuming that up is positive and down is negative. So we say, if we disregard air resistance, all objects fall towards the Earth with the same acceleration. And we can say we're going to call that free fall. So if we say the object is in free fall, then that's what's going on. And if I say the object is only acted on by gravity, that means it's in free fall. If I have a projectile, that's a two-dimensional thing, like a bullet being fired or a football being kicked or whatever, and I say it's a projectile, that means it's in free fall because we're ignoring acceleration we're ignoring the air resistance, and the downwards acceleration is 10 meters per second squared. So there's some colloquialisms or parlance, vernacular. There's a whole bunch of meaning behind some of the words that we commonly use. And as engineers, you're supposed to appreciate these words. So the more time you spend on task, the more you get into the language of it. A freely falling body is an object moving under the influence of gravity only, regardless of its initial motion. So this is, again, colloquially, fall means downwards. But we're saying, well, whether you're actually traveling upwards, if there's no air resistance acting on you and you're only pulled by gravity, you're in free fall. If you're at the top of your arc, top of your jump, and you're stationary, you're still in free fall because there's only gravity acting on you. And if you're falling downwards and there's no air resistance, you're in free fall. So sometimes people forget the upwards journey is also in free fall. Objects thrown upwards or downwards or those released from the rest are all falling freely once they are released. Falling freely. It's like, it's in free fall even though you're going upwards. Once they are in free fall, all objects have the same acceleration downwards equal to the acceleration due to gravity, which is 10 meters per second squared downwards. So typically, we'll say minus 10 meters per second squared. So, hidden information. I have a diver, and the diver has three choices. They can step off the edge, they can jump up, or they can actually pull themselves down. You can actually grab the diving board and pull yourself down. Three choices. In all cases, the acceleration is going to be minus 10 meters per second squared because you pulling. So I've got to be clear. Your journey as far as the free fall is concerned, which is the bit we're interested in, does not include the bit where you're pulling on the board. Because when you're pulling on the board, you have a force other than gravity acting on you, and so you're not in free fall. So these equations won't work. These equations only work when there's a constant force acting on you. And so these equations work from the instant you let go of the board to the instant before you touch the water or whatever. So you've got to be careful about where you start and where you end and not include bits that are not part of the free fall path. So a diver's acceleration is minus 10 meters per second squared throughout her journey. When the diver steps off a diving board, her initial velocity, vertical velocity, is 0 meters per second. Even if she runs and she goes like that, vertically, we're only talking about one-dimensional motion here, vertically, she had a 0 initial velocity downwards. The diver has the same speed passing a point on the way up and on the way down. We kind of talked about that in that previous sequence. If I'm at a certain height, so I start off with a certain upwards velocity, I've got less, I've got a certain value, I've got none, I'm given back that certain value. So whatever my speed was up, it's the same speed, but it's pointing downwards at the same height. There's a symmetry to these things. It takes as long to go from the board to the top as it does to go from the top level with the board again, because there's no air resistance. The diver has the same speed passing the point on the way up as on the way down. The final velocity of the diver is a velocity just before she reaches the point of interest. Now, often the point of interest is down here, so it's not when she has hit the water, it's as she reaches the water. Because as soon as she touches the water, there's a force of the water acting on her, and the journey, as far as free fall is concerned, is over, and the equations stop working. So I can't ask you about in the water as part of the journey. But I might not stop the journey at the end, and I might not start the journey at the beginning. I could ask you about, well, how long does it take to go to the top? I could say, how long does it take to go to the point on the way down? I could say, how long does it take, sorry, that should be end. I could say, how long does it take to get to this point, which is somewhere below the board? I could even say, how long is she falling for? And ignore the upwards bit. so I can start and stop my journeys at points in between where you might think. So again, diagrams become really, 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 really valuable. And then the other thing is that, and again, I'm a teacher and I'm a tester, and on teaching day, I'm your cheerleader and I'm trying to help you, and on testing day, I'm kind of cold and dispassionate, because I got to know that, have you mastered this skill? So what do? Well, I kind of like, I check. And one of the common mistakes is that people, if I say that the board is 5 meters high, and I say through various words, you're starting there and you're ending there. Many people recognize that that is a displacement of 5 meters. A subgroup of that will recognize that it's a displacement of minus 5 meters. Because if I start at the top and I end at the bottom, I went in a negative direction. Displacement is final position minus initial position, and your final position is lower than your initial position. And if you're using up is positive and down is negative, then it's got to be a minus displacement. And so, and that's something that, again, it's this attention to signs, and it comes with practice. So some people, they practice and they get it, and then they're like, they've got that skill. And for other people, they're still not quite there. And that's why, again, time on task is really important. Just do as many problems as you can. So again, though, I'm still tied by, we have these 4 equations, and I have to give you 3 out of 4 bits of information. So a diver steps off a high board. So here's the high board, and I draw it like that. Steps off the high board. The board is 5 meters above the water, so that there is 5 meters. And how long does it take her to reach the water? So I want my delta t. Let's make my list. So I want delta t. My initial velocity, she steps off the board, so it's going to be 0 meters per second. She didn't jump up, that would be a positive. She didn't pull herself down, that would be a negative. She just stepped to the side, so that would be 0 meters per second. I do have a displacement. I'm starting here and I'm ending here. I want the time of this journey, so I start at the beginning and I end at the end, and my displacement for that is minus 5 meters. Can you see where that comes from, that confusion comes from? And what else do I know? Oh, of course, I know my acceleration equals minus 10 meters per second squared. Notice that's not even mentioned in the question. It's like an intelligent person who's good at math, if they weren't practiced, might not think about acceleration. So it's not even mentioned in the question. That's the skill, basically. It's about visualization. And I'm going to say delta x is equal to vi delta t plus 1/2 a delta t squared. There's my a, there's my delta t, there's my delta x, there's my vi. Yeah, that's going to work. And so I know that minus 5 is equal to vi was 0, times delta t. Delta t is what I want, plus 1/2 times minus 10 times delta t squared. Oh, can you see how, again, somebody who's very comfortable at math, who looked at this equation would say, oh man, it's going to be I'm going to have to solve a quadratic equation because I want to find delta t. But because there's a 0 in there, it simplifies beautifully. So I get minus 5 over, let's take that to the other side, minus 5 is equal to delta t squared. So that gives me that delta t equals plus or minus 1 second. Now, if my clock starts at the top, then I know it's going to be plus 1 second. Yeah. So if you like, the physically correct answer would be plus 1 second, I suppose. I'd take either one in this case. What does that negative mean? the equation doesn't know, well, the equation doesn't know when you're going to want to start or stop. So it's going to give you, if you imagine this diver started off at the center of the universe and was traveling upwards and upwards and upwards and upwards so that she could be at the top of the diving board when time equals 0. And now she's traveling downwards, 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 downwards. So the equation will give you the time for her to go from that top to that bottom, but also there's the time to go the other way as well. So it does have some physical, the negative time does have some physical significance. It would be the time that the diver was down here if they were traveling on that journey, but they're not. So it does have some meaning, but it's not relevant in this case. Cool. Okay, can you, I'm going to pause this, and then can you guys have a go at that? Zoom. So let's continue and see what people say, and people basically all said C. So if you didn't see that, let's see where that comes from. So basically, I say a softball player throws a ball upwards. So I need to get I need to get you back, pen, and start you as well. Okay. So softball player throws the ball upwards, goes like that. The ball takes 5 seconds to reach the maximum height. So delta t for start to end, delta t equals 5 seconds. With what velocity was the ball thrown? So I want VI. And I want to make my list. So I'm going to say, well, VI equals, I don't know, meters per second. And A, of course, equals minus 10 meters per second squared. And delta t is equal to 5 seconds. And then I need one more thing. I either need a delta x or I need a VF. And oh, yes, reach the maximum height. Conceptually, I know at the maximum height when she's up here, she stops going up, the ball stops going upwards and it starts coming downwards. So VF would equal to 0 meters per second. So now I'm back with, let's have a look. Yeah, back with VF equals VI plus AT. It does come up often, but it's not exclusively does it come up. So that's going to be 0 is equal to VI plus minus 10 times 5. So VI equals, take the minus 50 to the other side, plus 50 meters per second. So that's nicely done. And then, can you have a go at that one for me, please? Cool. So we're back. Let's stop this. Let's have a look and see. So most people are saying B. There's a couple of others, but most people are saying B. So let's just see where that comes from. So we have a diver jumps. That's my pen. Sorry. So a diver jumps off a high board with a velocity. Oh dear me. Okay, it doesn't matter. Goes like that. And this upwards velocity is plus 15 meters per second. She reaches the water. Delta t equals 4 seconds. With what velocity does she reach the water? So we want our VF. So we say VI is equal to plus 15 meters per second. And I know from the start, which is my beginning there, to my end, which is just before she touches the water. So my delta t is equal to 4 seconds. I know my A is equal to minus 10 meters per second squared. And I want to know my VF is equal to, I don't know. Most common mistake on that is people will put down, think it's a conceptual question and put down VF equals 0 because it must stop moving. But again, that's not the end of the free fall. That's, once she's in the water. So we're going to say, let's have a look. VF squared equals VI squared. No. VF equals VI plus AT. Is that right again? VF equals. I got to put some different equations here. So VF equals, I don't know, VI equals plus 15, plus A is minus 10 times delta T is 4 seconds. So that's going to be VF is equal to plus 15 added to minus 40. So VF is equal to minus 25, I guess. 25 meters per second. And the negative sign, of course, means that it's traveling downwards. So there's my answer on that one. And I think that's the end of it. So there are 4 equations. I've got to give you 3 things and ask you for the 4th thing. Scenarios change, but it's basically the same issue over and over again.